Hi everyone, here we're going to cover everything you need to complete Project 3 that isn't already covered in one of the other videos, and probably a little bit of it we're going to end up covering more than once. So let's dive right into it. Here we have the data saved in a Google spreadsheet. You can see my first example data. We've played around with this before. This is statistics students' assignment grade versus their quiz and test grade from the fall semester, all randomized so you don't know who is who. So let's go ahead and graph this. So I'm going to highlight these two columns here in Google Sheets. I'm going to go Insert, Chart, and I have this nice scatter plot. Now what we see here is kind of that first possible category of data. It isn't super clear that these two variables are related at all. It sort of looks like someone just kind of sneezed on the page or flicked a paintbrush at it. They're all pretty spread out. So if my data looks like this, I'm only going to do one regression. I'm only going to do a linear regression. If it's not clear at all that the data are related in the first place, then it's certainly not going to be clear whether the relationship is linear, exponential, logarithmic, cubic, or something else entirely. There's no sense in doing all of those regressions if we haven't even answered the first question of, are they related? Sort of like before you answer the question of what flavor ice cream do you want, you have to answer the question, do you want ice cream? Well, we don't even know if we want ice cream. We don't even know if these are related at all. So I have a whole series of videos on how to do the regression, find the sum of the squares, the residuals, do the 100 trials, and I'm not going to redo that here. Instead, we're going to look at a different type of data, one where it's much more clear that they are related. I've labeled this Santa Fe population. This is actually Marin County population. Let's just rename that right now. This is the population of Marin County according to the census for the last 120 years. So again, I'm going to highlight my two columns, including the titles. I'm going to go Insert, Chart. Okay, now nobody would argue that the population here is related, is not related to the year. Nobody would claim this relationship is random. You might look at this and go, that's just random. There's no connection. It's completely random. You might look at that and you might in fact be right. But nobody would make that argument here. So here the better question is not, is population related to time? Obviously it is. The population wasn't random in every year. It kept increasing. The question is, what is the best description of this relationship? Is it linear? Is it exponential? Is it logistic? Is it logarithmic? Is it cubic? Is it quartic? Is it sinusoidal? That's the question now. What is the best actual connection? What is the best relationship we can find for this data? The two that you're going to do regardless are linear and exponential. And to be honest, a huge reason why you're doing those is because it allows you to demonstrate that you know how to interpret the slope and the y-intercept and the rate of growth or decay for those two types of equations. That, even though it doesn't necessarily fit the data very well, we're going to do those two for the practice interpreting them. The other one we're going to do is whichever one you think fits the data better, which for this one would be, he paused for a moment to give everyone time to answer, logistic. Definitely logistic. It's got that very clear logistic growth curve where it starts out looking exponential until sometime in the 1960s when it suddenly hits a cap and starts to level off. All right, now let's go through the process of actually finding the regression for this and graphing it here on Google Sheets. Double click on here. I'm going to go Customize, Series, and I'm going to choose a trend line. And look at that. There's my linear trend line. I could go ahead and copy this equation right over to my project, to my paper. I can also swap that out for exponential, and I can copy that. And there's my two graphs just like that. If I want to know what the equation was, I can just make that the label. There's my linear equation, 2,604 times x plus 0.0000496. That's times 10 to the negative 6. Or if I want to do that again with exponential, there's my exponential equation, There's my rate of growth or decay. Oh, and actually, I lied. Let me back up. This is not the same format as the exponential equation your calculator will give you. This is a different format of the exponential equation that makes the y-intercept and the rate of growth a little bit less obvious, a little bit harder to pick out. Now, here's the good news. This is the right graph. It's the right equation. It's just a different format than you're used to writing it. So we don't want to put this on your project. We can use the graph. The graph's great, but we don't want to put this on your project because this is the wrong format. So instead, we're going to go here to the emulator. We're going to go stat, calculate, exponential regression, L1 versus L2. If I want, I can store it to Y1, but it doesn't really matter because I'm not going to use the graph that my calculator gives me. Even the emulator's going to give me a pretty lousy graph that's not really worth putting on my project. Okay, here we go. So there's my A, my y-intercept, and there's my B, and if I subtract the 1, I've got my rate of growth right there, 2.8%. So there's the information, and there's the equation that I can include in the project. So we've just talked about the big two. We've talked about linear and exponential. We can get linear on either the calculator or Google Sheets. We can get exponential on the calculator, but we can use Google Sheets to map both of them, to graph both of them, excuse me. Now let's say I want to graph the logistic. Here's my problem. They don't have a logistic option here. I can do it over here on my calculator, and let's do that real quick just to see. Stat, calculate, logistic, L1 versus L2. I've already got something stored to Y1, so let's go ahead and store that to Y2. And there's my logistic equation. Oh, it's messy, but there it is. There's my logistic equation. And now if I want to graph it, let's go first to my stat plot. Make sure plot 1 is on. It's L1 versus L2. And let's do zoom stat to make sure everything shows up. And notice how this graph is matching my graph over here in terms of where the points are. That all looks good. How do I get this logistic graph onto something that I feel comfortable putting on my project? Because I don't want to put this screen on my project. It looks kind of terrible. I mean, I could do print screen and I could cut and paste this out, but I don't like that. So we're going to use another software to graph this logistic equation. We're going to use a software called Desmos. Desmos is free. Just go to desmos.com and go right into Start Graphing. Dive right into it. Desmos is free and it plays really nicely with Google Sheets. So I'm going to go back to Google Sheets and I've got all this data highlighted. I'm going to highlight this data. I'm going to copy it. I'm going to go here to Desmos and I'm just going to paste it. Control V for paste. Look at that. Just like that. Desmos graphs my data. It automatically zooms it. It automatically zooms my data to fit. This graph looks a lot nicer than the one on my calculator. It's got the grid lines. I can move around the graph, so I can make it kind of fit perfectly, and I can export the image. So I can download this image and then put it into my paper. It'll look a lot nicer this way. But I don't yet have the logistic regression. So I'm going to go down here to my second window. Now, Desmos will do a linear regression. It will do an exponential regression. It will not really do a logistic regression. It will, but I'm just going to steal it directly from my calculator. So let me go back to my y= screen where I have this regression, or actually if I just go to my home screen, nope, I don't have it anymore. Let's go ahead and run it again. Stats, calculate, logistic regression, calculate. All right, so now I'm going to copy this equation into Desmos. Here's the format, y equals. Adjust this around so I can see both screens at once and I don't have to keep going back and forth. Y equals C divided by, and C is 2.58652.1165 divided by divided by 1 plus A, and A is 2. Now it's 2.557. Let's do this. 2.255712174 E61. That's times 10 to the power 61. There's that. That times 10 to 61. A times E. Now that E is the irrational number E. 2.718281828. Desmos knows that. I can just put E. To the power. By the way, to do the power, I'm doing shift the number 6 to bring up that little caret, which puts me up in the exponent. Shift the number 6 for this little caret to get me in the exponent. In the power, open parentheses, negative B, B is 0.0722189554 times X. And that's just the letter X. Whew! That is a mess. That is an absolute mess, but there it is. Now let's go back to my graph. And there's my logistic regression. Simply copied directly over from my calculator, number by number. It's painstaking, but it works. And now I have a logistic graph that is worth putting on my project. Now I have a logistic graph that I can sort of zoom around on a little bit, make it so the axes kind of fit on the bottom of the screen. This looks nice enough to be worth putting in my project. While I'm at it, I might go ahead and do the linear and the exponential on Desmos as well. That way, all three of my graphs look the same. Instead of having one graph from Desmos and two graphs from Google Sheets, which will look a little awkward, I might go ahead and do all three on Desmos so they all look the same. Remember, this is just one component of it, showing the three graphs. Another important component is finding the sum of the squares of the residuals of all three. That can be done most easily on the calculator. It's doable on Google Sheets, but it's a lot easier on the calculator. And just for digs, let me show you really quick how to do it here for the logistic model. But I have other videos on this as well. This is just for your convenience. It's going to automatically do the sum of the squares, the residuals of the most recent, or I should say it's going to do the residuals of the most recent model I've done, which will be my logistic. If I want to do it for exponential or linear, I have to rerun a regression for exponential or linear and then do this process again. Stat, edit, go to an empty list, hit the up arrow so it says L3 equals down here at the bottom. Hit enter. Now it says L3 equals cursor. Tell me what to put in L3. Well, put the list of the residuals. They're a list. Second, list. There they are, residuals. Hit enter. Boom, there's my residuals for each of the logistic model. Remember, the residual is, in 1940, the actual population of Marin County was 52,907. The model predicted it would be 8,500 people lower than that. This is the difference between the actual population and the model's prediction. It's a measure of how wrong the model is. By how many people was the model wrong? If I do a total of all of these numbers, I'll have a sense of in total how accurate was the model. And the reason we do the sum of the squares of the residuals is that if we don't do that, the negative ones and the positive ones tend to cancel each other out. And if I don't want that to happen, I need to square them all first to make them all positive. To do the sum of the squares of L3, stat, calculate one variable stats, do it on L3, second the number 3 to bring up L3, calculate. There's the average, there's the sum, but this is the one I'm interested in, the sum of the squares of the residuals. This number by itself is relatively meaningless. Let's see, it's 1,214,130,195. So the sum of the squares, the residuals of the logistic model is about 1.2 billion. That number sounds totally meaningless, and it is. But if I compare it to the sum of the squares, the residuals for the linear and the exponential, and see which one's lowest, then I have a way of figuring out which of the models mathematically fits the data better. Not just visually, but actually mathematically. There you go. There's everything that isn't covered in one of the other videos and some of the things that are. Remember, if you are doing the first type of data where you're doing data that isn't clear whether it has a relationship at all, then you need to do the 100 trials to see what the p-value is. That is not in this video, but it is in the other ones. Make sure you watch those too.